Thanks, Lianping. So I hope no that much problem our product. Uh, my name is Zhong Ren. I'm a principal application engineer from Oxford Instrument Plasma Technology. Firstly, so my work is develop a process for device fabrication. So firstly, thanks University of Glasgow and Nanjing University of Science and Technology for hosting this workshop and gave an opportunity to us to share our experience with you about plasma processing to biomedical device manufacturing. So Oxford Instrument is a group company. Oxford Instrument Plasma Technology is I'm working for. So we supply the plasma tools for R&D and the industry. So our key market is power device, including the wide bandgap material, gallium nitride, silicon carbide, MEMS sensors, and optoelectronics, including laser, LED detectors, but also nanotechnology, including 2D materials, graphene, MOS2, WS2, etc. Biomedical area, including microfluidics, coatings, and advanced materials. Semiconductor technology became increasingly important in global healthcare, enabling novel understanding, discovery, and treatment of disease to make healthcare more affordable and efficient, both in and out of a clinic. So lab-on-chip devices enable faster, cheaper, and accurate analysis for health diagnostic, as well as life science R&D. So, this emerging market is grows strongly. So biomedical device, class of miniaturized electric device. So assembling with the integration with supporting signal processing electronics. So plasma technology. So we provide etching tool for microfluidics, sensings and transducer layer deposition, but also protect coatings. Microfluidics has been mentioned by Professor Marsh and other speakers in early talks. Microfluidics was manufactured on silicon, glass, and polymer, including plastic and photoresist. The very first integrating the devices was based on silicon substrate, followed by glass, which gives some advantage. So process control over channels dimension and the surface morphology. So fabrication technique provide cost-effective maintaining processing, creating devices that remain functional over long-term use. Silicon can be etched by any halogen atoms, but only fluorine react with silicon spontaneously. That means need a passivation to maintain vertical profile. So Bosch process, I believe you all know the Bosch process. Bosch process used the alternating sequencing of deposition and etch. At the three-step Bosch process, the first step is deposition, and then breakthrough step remove the polymer on bottom, but keep polymer to protecting side walls. So isotropic at the last, repeat cycles to etching deeper. So Bosch process gives a high rate, high selectivity, and a highly volatile profile. So it's a dominant process in MEMS application. So Bosch process so usually used to etching features over 1 micro and the depth over 10 microns. Cryogenic silicon etching is typically used for smooth settables and nanostructure etching. So mixed gas process are another option for shallow, low aspect ratio features. So Bosch process gives a high rate, so it's suitable to etching micro-scale devices. And the smooth settables utilizing our fast switching capabilities. So in the real device fabrications, usually trade off the etching rate selectivity for enhancing high aspect ratio and smooth settables. Cryogenic etching need liquid nitrogen iron 2 to cooling lower electrode temperature to minus 100 degrees C. The high dense plasma forms a fluorine radical to etching silicon. Low bias clear polymers is a silicon fluoride oxide. This is only the passivation at a lower temperature, minus 100 degrees C. And to keep the bottom clear, but protect the unsettable, which gives a good selectivity to mask photoresist and silicon dioxide. So the process can control taped or vertical profiles. So this is a trained process trained data we studied with calibrator in RBNL US. So 3 key parameters: oxygen flow, temperature, and RF bias power. So we can control the profile from left-hand side is a positive sloped profile, to the middle is a vertical, and undercut and retention profile. So 3 parameters usually can compensate each other. So that means from the positive profile to vertical profile, we can reduce the oxygen flow or increase table temperature or increase the RF bias power. The key point to take from this slide is etching high exposed area. This is an application for microfluid disk or wire reveal process. So the process gives a good uniformity across the wafer, but also maintains smooth settables. Right-hand side SEM image show the micro pillars array. It's uniform, good uniformity across the wafer. It's made for a microfluidic filter. 3 typical silicon etching processes can be run in a single chambers. So left one is a Bosch process. So middle one is a cryo process, and the right-hand side is a mixed gas process. So 3 methods can make similar micro or nano size pillars. To etching glass or coarse materials usually need a metal mask for high selectivity. So the chromium metal is a suitable mask material. And so we need etching the metal mask by plasma first. So optimize the ICP mode process gives a vertical profile, good uniformity. So selectivity to PR mask is over 1:1, but a very high selectivity to silicon or silicon dioxide, over 1,000:1. So the ICM show the vertical profile on silicon dioxide top. So because I think I'm last speaker, if you have any question, so we can discuss, because this is a workshop. So please ask. So glass commonly used where insulating substrate or photonic element. So typically, we use the fluorine-based plasma to etching quartz or glass. So 200 to 500 nanometer per minute etching rate depends on the aspect ratio size. The higher aspect ratio usually you're etching slow jobs with good uniformity with a metal mask. So glass with impurity, so that impurity is involatile species, so need a high ion bombardment to remove them and keep smooth base. So etching rate selectivity slightly lower than coarse material. So you can see the ICM show the slightly sloped profile. Polymer enable cost effective and low auto fluorescence. ICU8 is an IPC-based photoresist, which has been widely used for high aspect ratio maps application because it's very good mechanical properties, water impermeability, dielectric nature, but also compatibility with semiconductor fabrication. Polyimide PI is an emerging candidate material, which also have a good biocompatibility and chemical resistance. But this material has a very high glass transition temperature, up to 325 degrees C. So as etching SU8, so we are using the similar oxygen plasma-based process to etching polyimide. So some polymer contains silicon, so we mix some fluorine gas to remove this silicon-based material. Metal mask gives high selectivity. Control surface property is a key requirement after the creation of channels at biomedical devices. So about the silicon modifications. For example, a silicon substrate with silicon dioxide on top is a hydrophilic surface, while PMMA surface is a hydrophobic. So tuning this property over the device surface enables control over fluid flow and interaction. Organic thin film can be deposited by vapor deposition. Black silicon is another surface which is attracting lots of interest in the recent past. Black silicon is a composite of nano-structured silicon, looks like nano needles or nano specks. Black silicon can be made by plasma etching process based on SF602 or SF6C5A, even Bosch process. So different methods made a different topographic. So you can say if the water drop on black silicon surface, they keep the purely round because the surface is super hydrophobic. Sensing and transducer layers fabrication needs a thin film deposition process, like PCVD. I think your GWC have PCVD 25 years ago. Also the ALD, you also have ALD tool from Oxford. It's an atomic layer deposition. As a crucial component at biosensors, A sensing layer specifically identifies target biomolecules within the isotype. So converts the sensing event into electrical or electrochemical signals. So devices are often FET based, which require several layers of process. So this layer usually is oxide, so it can be deposited by the PCVD and ALE. The other material has been reported and studied. Depends on sensing strategy and target. So I will talk some typical material later. So ALD and PECVD can deposit thin film oxide like aluminum oxide, titanium oxide, and silicon dioxide at a lower temperature using oxygen plasma or ozone. So plasma and biosyn also gives the option to tuning properties, including crystallinity, and stress. Plasma ALD can deposit high quality titanium oxide film. So reference index usually be used to detect material density and quality. So higher reference index indicate better quality film. So you can say using plasma ALD at 100 degrees C, the reference index is similar to thermal ALD at 200 degrees C. So this proved plasma ALD give a better film quality. Tantalum oxide is usually used as bias layers. So it also can be deposited at a lower temperature, 90 degree. So film stress can be adjusted by bias power. A tensile stress without any bias power. So with bias power, so stress becomes compressive. So you can see the data. So at a higher temperature, we developed process gives low impurity titanium oxide ALD film. So in the data from the SIMS at the right-hand side, so the film deposit on silicon surface. So you can see very low signal level of carbon and nitrogen. This is an example. It's a origami robot, so made by combining ALD and graphene. So unfolding and refold in response to pH changes. And they close later. Okay, so how they made the device? The glass contracts expands when exposed to a change in pH or temperature compared to graphene. So this effect is used to make structures that can bend. So there is a process flow using ALD to deposit alumina and silica films. White transfer graphene on top of a stack. So photoresist make photoresist mask, and then etching the structure. Finally, release the structure in white etch. This is another example. Is made optical fluidic sensor. the rolling up the process of 16 nanometer thickness titanium oxide membranes, so patterned 50 by 50 microns, then do photoresist removed, and roll up the film to microtubes. Afterwards, coating with ALD for high quality titanium oxide. It's a small video show you the rolling up the membrane to be microtube, 50 micro length with a 10 micro diameter.
How thick the film?
The film is thick to is a 16 nanometer thickness. So photonic sensors relate on change in electromagnetic field during biosensing. So integrated photonics and plasmonics structures are mostly commonly employed. So basically, this is talking about silicon photonics platform, but also integrated with compound semiconductor devices. So state-of-the-art silicon waveguide fabrication combines the e-beam or deep UV lithography and subsequent plasma dredge processing to transfer pattern into SOI device layer. The top thickness is about 200 nanometer, and some shallow gradient etching only 70 nanometer. So the process required smooth cycles for low propagation loss, low etching rate for accuracy control, and high enough selectivity because that's limited by mask thickness, but also notch control at a silicon dioxide interface. Using SHQ mask, we're using RE mode cryo etching. We achieved higher selectivity, 4 to 1. The selectivity 4 to 1 is high because the etching rate is very low. It's down to 20 nanometer per minute. More complex devices has been made by Sun Yat-sen University in China using extract tool. They made subvalence grating couplers, thermally tunable grating coupler, and the MIME-based silicon grating couplers, optical vortex emitter. Micro cantilever is extremely sensitive structures in MIME's devices. This is very widely used already in the MIMES area, but also quite useful for the biomedical devices. So locally perform label-free molecular recognition and management with high resolutions. Transduction based on the resonance frequency changed or using the piezo resistance phenomena. Nanopore devices can long read the DNA, RNA single molecule sequencing and sensing devices. So transduction based on electro or electrochemical interaction of bases with the nanopore. So process challenging point including stress control of coatings, heat management due to etching because we talk a lot of material is polymer based. Polymer don't like high temperature. So ion bombardment from plasma etching usually heat the surface. So we need a good heat management. The low damage conformal coating on membranes, graphene and 2D materials synthesis. This is a general question when we're talking about graphene, because the big area graphene transfer is quite difficult. A key point to take from this slide is etching from backside membrane. The low process for control, low etching rate process for control with low or non-helium backside coating. If you use any plasma tool, you know there is a parameter you set to backside helium, and the backside helium help transfer heat from the sample or wafer to lower electrode. So adjust the process maintains the good profile with a clean sidewall, particularly at the corner. Usually you see long striation on the sidewall at the corner. So the ICM shows etched cantilever structure. Protective coating provide longevity for devices. Stack of silicon nitride and silicon dioxide, hafnium oxide is a high K material, layers for moisture protection. So layers with a low water vapor transmission rate to increase longevity of devices. Low temperature processing using plasma enhanced deposition. Biocompatible coating protect everything your device. So the layer for in vitro as well implantable devices. So plasma activation of surface is to ensure strong bonding to substrate, provide effective plasma cleaning of microfluidic channels. The plasma on, then another wafer bonding on surface. Exposure to oxygen plasma enables adhesive transfer by masking the surface more hydrophilic. Plasma treatment also helps in creating an irreversible PDMS bond. So I think the other talk from Nanjing Professor Han already showed lots of interesting structure based on the PDMS structure. So this method without any anneal. Removal of polymer scum using reactive plasma, so to make a very clean surface without contamination, but also maintains the original channel profile. So in a summary, so Oxford Instrument plasma technology provide a plasma solution for biomedical devices, include etching, microfluidics component, making sensing layers and devices, providing the hermetic and biocompatible coating. So I think GWC already have most of the system from us. We supply the plasma tools, including deep RE tool for silicon and oxide etching, SP and RE for general etching, PCVD and ALD for thin film deposition, ion beam tool for both etching and deposition. So at last, I'd like to thank my colleagues in both applications and technology teams at Plasma Technology, but also all our collaborators. Thanks for your attention. Any questions?
Thank you.
Yeah.
Any questions? So, for your metal masks, normally you use wet etch or dry etch, or
We are using dredge because we are plasma technology. You also can easily use white etch, but white etch you have limitation. Some metal you are hard to get suitable etchant. So plasma can give you better profile control without undercut. So dry etching need very accurately control the etching time.
Large inside have any questions?
Can you hear us?
Yeah.
I got it. The question is,
Please repeat your question.
the noise is suppressed, yes. Is there any difference for etching a gold metal film and a silica surface? Does it have any difference in the undercut?
So the
When
question
you
is,
Hi, can you hear me now? Hello. 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 Can you hear me?
Yeah, we can.
Good now. So what's in the plasma selections? Uh, do you make any difference when you etching a metal film, such as a gold film, and just the oxide, such as silicon?
so the question is etching the gold film by plasma.
Yeah. Does it differ from?
So yeah, we use a different chemistry and process to etching different metal film. So chromium easy to be etched by chlorine and oxygen. This is quite chemical etching. So some metal is very hard and involatile. So we're using the argon sputter etch.
Okay. So all your machines are just plasma etching.
So mainly based plasma technology. We have the ion beam tool, is the high BIOS, the ion etching and deposition.
Thank you. Okay, thank you.
Thanks.
So another question for our cluster is ALD is a thermal plasma or is plasma ALD or thermal plasma?
The hardware is a plasma ALD, but you can run thermal process without the plasma because the table temperature can raise up to 400 degrees C. So for the aluminum oxide or silicon oxide, easily you can do the thermal. But for nitride, you need a plasma to help, and metal you need a plasma as well.
So I think John, because he is the director of JWNC, at the moment, our three guy on the cluster, yeah, it's very difficult to get a very good recipe to dry etch, for example, the sidewall grating, because we have not found the window, the recipe for the window has a little bit of higher etch rate and also good sidewall of the grating. You know, at the moment our etch rate is very slow. It's maybe use CH4 hydrogen and
Yeah.
oxygen. We, we still is a lot of our PhD student and the PDLS has this problem. So maybe if your Oxford instrument can.
We are happy to support you, no problem.
Yeah.
Yeah, so we can discuss detail, I
Yeah.
think. Yeah.
This is also we take away a lot of time, you know, to sort out this problem, you know.
I have a question.
Yes, please.
One question. Actually, I want to improve my number one device performance, so I need to deposit use the ALD technique. There's some oxidation layer to surface passage. Well, surface passage has a specific location, and I was told that when I try to use ALD, because ALD is kind of high temperature thing, So I want to protect.
Depends material.
Yeah, depends on the material.
Yeah.
Okay. And I read the paper. It's about use the E-beam to do the ALD, which is called the low temperature.
E-beam can do deposition as well because E-beam is shine on the target and then redep on the sample, so the sample temperature will be lower. But for the oxide or aluminum oxide, you can do room temperature process. So, but the sample may be slightly higher temperature than room temperature. The table is room temperature. Usually people control temperature on the table, I mean the lower electrode, rather than the sample.
So my question is that possible? I can just spin coat my sample with some, like the photoresist
Yes.
and pattern the design what I need
Yeah.
to do the low temperature ALD.
Yeah, you can do. You do the photoresist pattern and expose the area you want to deposit. And then you put a sample in the ALD chamber, you do the deposition, and then you control the time to the thickness. ALD is very good conformal coating technique. So basically, you can hold your nanowire and show your device, and I don't know the material you use on the nanowire, but yeah, but basically all the material is okay to coat it, yeah, by ALD film. But that depends the thickness, and because ALD is atomic layer deposition, so from the name you know the time is longer because they do the atomic layer and atomic layer. So the a few nanometer thickness would be okay. Yeah.
So Nanjing side, if you have any more questions.
Any more questions, guys? I don't think so. Thank you.
Okay, thank you very much. So for today's session, we are finished. So for the dinner, we are Chinese restaurant.